Okay, as we continue, we're going to sum up the forces in the horizontal direction per unit length of the wall. So basically, summing up the horizontal forces, that would be the pressure of the diagram, the area of the pressure diagram AC, ACDE, minus the area of EBF, minus the force on the anchor rod, and equal to 0. So of course, F is the tension rod, is the tension in the anchor rod. So from this, we can have this equation, P minus 1/2 sigma sub 8 times L sub 4. So this one minus F, meaning to say your area EBF would be equal to this area, and our P, actually, this P is equal to the area of this ACDE. Or we can have this equation to compute for the force acting on the tie rod. So basically, if we now take the moment about point O prime, which is the location, O prime is the location of your anchor rod, we can have this equation. And based on this equation, we can have can simplify through this expression. And you have to take note that D theoretical is equal to L sub 3 plus L sub 4. So basically, from this equation, we can compute for L sub 4. Substitute the given known variables or parameters. And based on the theoretical depth of penetration, we can compute for the actual depth of penetration, which is increased by 30 to 40%. So that would be 1.3 to 1.4 of the D theoretical. So from here, the maximum theoretical moment to which the sheet pile will be subjected occurs at a certain depth, Z equal to L1 and Z equal to L1 plus L2. So meaning to say, our maximum theoretical moment of the sheet pile is will occur between L1, between Z, which is equal to L1 plus L sub 2. And we can have the maximum moment through this equation. It can be evaluated using this equation, wherein the depth Z for the zero shear and can be used to evaluate our maximum moment. So once the value of Z is identified, the magnitude of the maximum moment can be also be identified. However, there are cases where in the dredge of the line of the slope is not horizontal, so there is a slope. It can be, the dredge line can be sloping, can be sloped at a certain angle. So for this one, this is an illustration for a dredge that is sloped at a certain angle beta with the horizontal. So in that case, our coefficient for passive pressure, this one cannot be used. So we're going to have a variation for the case of P, or the passive pressure coefficient, using this figure. We just have to get the value for beta and the angle of friction so that we can have now the value for our passive pressure coefficient, the Coulomb passive pressure coefficient, using this figure. So we have here a sample problem. You try to refer to our figure 9.14. So this is our figure for our sample problem. Our L1 is 2 meters, L3 is 3 meters, I sub 1 and I sub 2 are 1 meter, C prime is 0, Phi prime is equal to 32 degrees, and gamma prime is 15.9 kilonewton per cubic meter. Saturated unit weight is 19.33 kilonewton per cubic meter. We're going to compute for the theoretical and actual depth of penetration, the anchor force per unit length of the wall, and we have to determine our maximum moment. So for this one, we have to identify our case of A and case of P, that is 0.307 and 3.25 respectively. So therefore, we can compute now for sigma sub 1, sigma sub 2 using this equation. So we have 9.763 and 18.53 kilonewton per meter squared respectively. So using this equation or expression, you can compute for L sub 3, which is 0.66 meters. And our P, the force acting on the total force acting on the sheet pile, is equal to this equation. We try to substitute L1, sigma sub 1, L sub 2, sigma sub 2, and L sub 3. We get now 58.32 kilonewton per meter. And we take a moment about point E from our figure 9.14. We get now Z bar, and that is equivalent to 2.23 meters. And you can have this equation so that you can compute for L sub 4. For L sub 4, we have to take note that our L1 and L2, this is in the position wherein our anchor rod is located. L1 is above the anchor rod, L2 is below the anchor rod. Our K sub is 3.25, K sub is 0.307. We substitute to this equation so that you can have our L sub 4. So you can solve for L sub 4 by trial and error. You just have somehow, by trial and error, you can have an assumption for L sub 4. If it satisfies the equation, which is equal to 0, then you can have now the value for L sub 4. So basically for this, as we have the trial and error process, our L sub 4 here is equal to 1.4. So our D theoretical is equal to L3 plus L4, and L3 a while ago is 0.66 plus L4 1.4, that is 2.06 meters. And you can have now the D actual, which is 1.4 of 2.06, you have 2.88 meters. And you can now compute for the force on the anchor rod, which is equal to this equation, that it gives us 30.86 kilonewton per meter. And for the maximum moment, using this equation, try to simplify this one so that we can compute the maximum moment. We just have first to compute for our Z. So for this equation, if we try to simplify, let us have a simplified form. We can have Z minus 2 equal to X. And if you try to substitute Z minus 2 equal to X, we have here X. When you try to simplify, X is 1.72 meters. And based on our assumption, or we let Z minus 2 equal to X, you simply have to substitute this value so that we can have the value for Z, which is 3.72 meters. And if we're going to check, the 3.72 is in between L1 and L sub 2. So if you try to take a moment about point 0 shear force, wherein our value for Z is 3.72 or X is 1.72, you can now have your maximum moment, meaning to say you get the area of the you have the area of the pressure diagram multiplied to the moment run distance from the center of the area of the pressure diagram to the point of 0 shear. So we get now, if you try to simplify this one, we get our maximum moment to be 43.72 kilonewton meter per meter. So for this one, point of 0 shear, you refer to our figure. So we have here. So this is the point of 0 shear. This would be our reference point using the pressure diagram so that you can have the maximum moment. Now we move on to moment reduction for anchored sheet pile walls. Sheet piles are flexible, and hence sheet pile walls yield, so it becomes displaced laterally, so which redistributes the lateral earth pressure. So this change tends to reduce the maximum bending moment as calculated by the procedure outlined in the previous discussion. So it was suggested by Rowe for the procedure for reducing the maximum design moment on the sheet pile walls obtained from the free earth support method. So this section discusses the procedure of moment reduction for sheet pile penetrating into sand. So we have here an illustration for a sheet pile penetrating a sand. So we have to plot our log sub P, our log of rho against M sub D over M maximum. This is having a loose sand and dense sand and gravel. So this is the procedure according to Rho. You have to compute for H prime the total height of the pile driven. You have to compute the relative flexibility of the pile, Rho equal to this equation. And you have to identify your design moment, identify the maximum theoretical moment. Then, so we have here, this Rho is is in English. So our E here is in feet, pounds per, our H is in feet, E is pounds per square inch, I is inches to the fourth all over feet of the wall. So the procedure for the use of the moment reduction diagram. So we have here, you're going to choose a sheet pile section. You have to find the modulus S of the selected section per unit length of the wall. You have to determine the moment of inertia of the section per unit length of the wall. You have to obtain H prime and calculate rho. You have to identify your log of rho. And you have to find the moment capacity of the pile section. So moment capacity of the pile is given by this equation. And you have to determine your MD over Mmax. Okay, of course, Mmax is the maximum theoretical moment as previously determined. You have to plot your log of rho and your M sub D over M sub max using this, using the figure as illustrated a while ago, figure 9.22. Then, of course, you have to repeat as step 1 to 8 for several sections of the sheet pile. So the points that fall above the curve in loose sand or dense sand, as the case may be, are safe section. So meaning to say, if the points will lie above dense sand and loose sand, they are safe section. Below this, they're unsafe section. So for an anchor sheet pile penetrating into sand with a sloping dredge line, a moment reduction procedure similar to that just outlined may be adopted. So we have here a sample problem. We're going to use the previous example wherein we have computed our maximum moment, which is 43.72 kilonewton meter per meter. And we're given for this example E, which is equal to this, and allowable pressure is equal to this value. And you can have the value by having in tabular manner. So you have to identify the pile, you have to identify the section of the sheet pile. We're going to have your I, identify the I of the identified pile section. We have identified our H prime, which is 7.9. We have our rho. Simply have used this equation, log of rho, which is equal to this. And our section modulus for this section is equal to this value. So therefore, our MD, which is S times the allowable pressure, is equal to this value. And now we have MD over Mmax, which is equal to this. Based on our illustration from this table, it is sufficient. Our PSA 31 is a sufficient section. So which is, we have to use this PSA 31 section. So since this is, because if you try to observe, if you try to graph log of rho and MD over Mmax, you have here the position of PSA 31, PSA 23. So based on this illustration, our illustration satisfy the minimum requirement of PSA 31. So for this one, the smaller in value, we're going to choose that one. So which means that the value here is sufficient enough. So we're going to use PSA 31 for this particular example. So the section is PSA 31. So we move on now to free earth support method for penetration of clay. So figure 9.28, this one, shows an anchored sheet pile wall penetrating a clay soil and a granular soil backfill. So basically, we are now on free earth support method for penetration of clay.